Hey everyone, good evening and thanks for being here. Thank you to the DET community and also for Jenny and Microsoft for having me here. Um, I am a data engineer here in at OpenAI in the safety systems team. Um, I have about 8+ years of experience. I've worked with Google before this. I've been there for 4 years, and before that, I was at Twitter in the trust and safety team. So, today I'm going to present a little bit about the data engineering behind classifier evaluation. I'm not going to spend a lot of time going through like the classifier training or like any mathematics or statistics behind the metrics. We want to focus like more on the system behind them, like how the data is sampled from the production, how we run like distributed inference and sampling, and then collect that delayed evidence and reproduce that decision later. So the central question here is how do we make evaluation like trustworthy when the data arrives at different times? I'm going to give a little bit of introduction of what a classifier means. A classifier is just like produces a score when you provided some kind of input, and that input can really be like a single message. It could be like an entire conversation, or it could be like the last 5 or 10 turns of a conversation. And when you're building like a classifier, maybe for the financial world, it could be like a lot of scores or user persona and so on. So the important thing to see here is the classifier produces a score, and then the policy sets the threshold. So when you apply the threshold to the score, you might get a positive or a negative on the labeling. And based on that, there are some decisions which are taken, which could be a block, flag, or maybe even like escalate to another classifier. So the top level metrics, I won't go a lot detail into that. It's just like the precision and recall and a lot of other metrics. The recall is just like say how much of positive examples can your classifier actually capture, and precision is like how precise is that capture rate, right? And over here you can see in both of the denominators, the ground truth plays a very important role. So imagine we have like a data agent, like say it just produces some kind of a metric saying that the recall for the shadow classifier has improved. Do we trust that metric? We can, but we need to know like some of the main questions here. Like, did both the versions, which is the production and the shadow version, actually see comparable population? Can we even identify like which was the model snapshot, what was like the features used, and what are like the sampling versions? And do we even know that all this evidence actually arrived, or are we comparing like one complete data set with some other like incomplete data set? So the most naive way is we have, say, for example, a live request. I just named it as an evaluation item ID. It could be anything, which is like maybe message, conversation, as I mentioned before. And then the production classifier runs, right, with for all the requests. And then you have a shadow classifier. Maybe we fork like say 10 or 20% of the data to the shadow classifier. The downstream ETL here is pretty simple because we just pair it by the evaluation item ID and then we evaluate the scores. So this is mostly like an A/B test, but here we don't do like any kind of randomized product experiment. But one thing to note here is like the forking process is actually governed by some sampling algorithm. It could be, say, for example, a bias sampler, and a bias sampler is just like maybe you are just like sampling for high severity use cases. This is great, but we want more. So in the research space, I know all of you must have heard that human labels are like the ground truth. Research teams spend hours and hours of data trying to get like experts label the human data sets and then use it like for training. We are going to make use of those data sets as well to evaluate the shadow classifiers. And then the other thing that we have is we directly like sample after the production events have landed. We select like some kind of a representative or informative subset, not just like a bias sampler. you want to collaborate like very closely with your data scientist team to understand like what are like some of the sampling methodologies they are thinking. Are you able to extend the design and so on? So the rest of the talk here is going to mainly like focus on part two, but I can give a brief introduction of how part one works as well. So say, for example, you have this human data set. We want to replay that same data set through or the conversation through like a production or a shadow classifier, and then you can evaluate the scores. It's pretty simple, right? The second one is where like you have a lot of issues because it's completely like asynchronous. The events land late and everything is like, it's handed over to another task. So now I'm going to introduce like a very important orchestrator here, which is like Flight. Flight is very similar to Airflow, but it's a Python native orchestrator which can run like containerized Kubernetes. Here, there are like some concepts here which I try to add. Like say, for example, there is a task. Task has like a fixed input, a fixed output, and you could also provide like some kind of heterogeneous pool. Like say it could be a CPU pool or a GPU pool. And then you have a workflow, which is very similar to an Airflow DAG, where you can like chain different tasks together. And then you have a launch plan. A launch plan is just like a saved and a version way to invoke the workflow. So this launch plan here becomes like a very useful entry point. I'm going to explain a little bit more onto that in the next slide. So a caller of this launch plan really don't need to know any of the implementation details. They can just stay abstracted from the implementation details in the launch plan. So the flight here is really like not moving any kind of like data. It's just for the control plane. Most of the like the compute is going to be done by Spark. So at this point, I would like to ask in this room, like I know most of the people here are data engineers. Do everyone like use Airflow here? Okay, I see a few hands. So we here don't even need to like replace that life cycle. Airflow can still like own your production clock. It can have like sensors, execute the task like whenever the partition is ready, kind of govern your retries, SLA, and then publish the data. But Flight here gives the data scientists like an execution boundary. So they can actually package their sampling logic and its dependencies without even taking ownership of the entire like production Airflow DAG. So Airflow can just launch the pinned launch plan that I showed in the previous slide, and it can just like wait asynchronously. Like your DAG could just pass, it just like submits a batch. Yeah. So maybe now, like, let me go on to the next slide. So imagine, like, as I mentioned, a data scientist wants to add a new sampling strategy tomorrow. Today, maybe we go in, like, say, with an XGBoost risk sampler. Tomorrow, it would be important sampling, uncertainty sampling, what not, like stratified. I'm not a data scientist, so I really get like confused by all these terms. But yeah, we do not want like a new production task or like even like a production DAG for each of these sampling methodology, or even have like multiple tasks in the same Airflow DAG. So all that we want from the data scientists is to implement like a contract where they can provide us this launch plan and kind of like package the dependencies in a container. So the workflow in Flight is registered, and then we can just invoke the launch plan from Airflow. The platform idea here is like pretty simple. We want to keep the design and the strategy as extensible as possible and as experimental as possible till the data scientists get more confidence in their metrics. Now I'm going to a little bit like zoom in into like say for an example for XGBoost. Okay, so whenever like a data scientist registers an XGBoost model, they just like train it in ad hoc notebooks and kind of like register it like in say maybe like MLflow. But what about the retraining process and how you want your feature set to be as new as possible? So the one thing that we can do is we want Airflow to still own the schedule. Spark, it can produce like the feature data set. So when I say features, it's not just like, some kind of numerical features from the classifier. It could also include like text features from your data. And also, say, for example, you have like categorical variables. You might have to do some transformation, do some one-hot encoding, kind of convert it into numerical score so that it's just like easier for inference. So yeah, once we launch Flight in the training mode, it trains the Spark XGBoost classifier, and then we have like a 5% like holdout data with which we have like a lot of data quality gates. So we work with you can work with the data scientist to see like the area under the curve, F1 precision, or other kind of metrics that they're interested in. And then we do like a kind of a passive data quality check. Like we don't stop promoting it to ML flow, but rather you could just like persist the data quality metrics but still promote the champion sampler. So the one thing about this one is, since this is an offline flow, we are not like calling like any endpoint for doing the inference, right? So we need to bring the model to your Spark in order to do the inference in batches. So say, for example, after you have trained this pipeline and you have like a more like refreshed XGBoost sampler, your Airflow like maybe runs like daily. There's a closed partition. It wakes up, again like calculates the Spark features. It could share like the common utilities that you use for the training. And then here, same way, it could invoke the Flight sampler, which is the launch plan, but this time it would be in like inference mode. Here, I should have explained this better. Like I just added V18, V19 because V18, you can consider that to be like a production classifier. V19 is like a candidate classifier. So all that we do is we take these 5 billion raw events that happen in production every hour, and then we do like a distributed scoring inference on that. So this has actually caused like a lot of out of memory errors for us, which I can explain in the next slide. But what we're trying to do here is, after running the shadow, we can look for disagreements between the production and shadow and kind of do an async handoff to like LLM grading, or maybe even like human labels as well. But the capacity for human labels is usually very less, so we kind of go in with like LLM grades. Uh, Yeah, so here I'll not explain a lot of like all the four. So I can explain the first one and the second one. So if the model is already registered as a Spark native, you can just start with the Spark XGBoost classifier model and use like all the methods under that. But say, for example, in our use case, it was registered as a launch plan and it's more like Python native. So in order to support the vectorized prediction, you'll have to enable some kind of settings and also make sure you're doing some changes to like from your Parquet to like a columnar format, which is like an arrow format that is used to exchange between JVM and like the Python. So for that, you'll also have to make sure that you'll also have to make sure that you set the arrow batch to a nominal level. For this, you can use like all of the coding agents that you have to make sure like you can say like what is the level of traffic that you're going to run inference on, and what are like some of the modes you need, and what is the batch size that you could set, and so on. And the other two, I'll not be explaining that because that is more like for streaming mode. Okay. Now, this is the most like critical part. Here, we more have to do a lot of decisions for downstream data engineering. Say, for example, you take all the events from a 10 a.m. production window. The events arrive between 10 to 11. Spark runs like, creates these feature sets, runs the sampling, and then the selected items actually go through shadow, and then there is an asynchronous process of LLM grade and so on, right? So say, for example, if your grade arrives at 1 p.m. for a 10 a.m. production window, how should we handle it? Do you? Anyone can answer? Okay, so we can have two layers here. So maybe we can have something like a raw evidence layer where we append whenever a grade arrives. So this kind of helps to preserve like what happened in production, right? Like what happened after it was graded. But then we could also have like a reconciliation job that reads these append only facts, and then it produces like a kind of a table that is tied to the production hour. So one thing to note here is we don't need to merge for every grade because it would cause like a lot of issues where you will have like small files, and then like you keep on doing these atomic commits and it gets like very messy. So it's very important that you kind of take these changes that you find in batches, and then you are able to do it in the merge only mode. So once these historical partition, they receive the new evidence, backfill kind of becomes like easier and not a very big like pain point. So I'll explain a little bit about backfills in the next slide. See, the previous slide showed like how late evidence is reconciled into like an original production hour. Now let us think of a situation where like again the data scientist comes to us and asks like we want this new sampling strategy to run like for maybe again like for the previous week. So how do we handle such scenarios? We want our data to be idempotent, which means like when we have the same set of input, even when you backfill, it needs to produce the same output. But the way we treat this is like having a new sampling strategy and trying to run it for the past week is a new identity. So we want to make sure we embed this identity during the sampling run, so in that way, we can trace the sampling identity across like the production hours and even when the LLM grades like land later. So this kind of distinction is really important here because the retrying is actually the same intent, but when you are retrying it with a new sampler, then it becomes a new intent. So we do expect that there would be new rows in that hour partition. Okay, so right now I'm also going to share a little bit of learnings from this project. So the first thing I want to say is Airflow here can own the data readiness, right? Like we want to make sure we are separating these kind of orchestration responsibilities. Airflow can own the entire data flow, but Flight can still give a computational layer which multiple people in the team can actually collaborate with the data engineering team even without even having to change the production data pipeline that we have. Second, what we want to make sure is to make this like as extensible as possible. You need to listen like when there are like multiple shadow classifiers running and we want to launch immediately, it's really like not possible. You need to go back, you need to rerun like for the past week and then report on the results. So we want to make sure that this system is as extensible as possible, able to handle the backfills, retries without creating duplicates in your fact tables. Um, yeah, so the other thing that I want to say is like I know like a lot of our data is now backed with a data agent. So having like this kind of infrastructure that really helps you to replay these pipelines would give you more confidence in the results.